Okay, Schweitzer, quick little update here as far as what is the pH when after acid and base are mixed. So there's a couple steps here. First thing, we have to allow the neutralization reaction to occur. So step one is going to be to neutralize. And in this case, let's say we're doing HCN plus NaOH. Now we're either going to do a weak acid and a strong base, or it could be a weak base and a strong acid, or a strong acid and a strong base. These things, the strong, will react very vigorously. If you had a weak acid mixed with a weak base, that is usually the result of one of these neutralizations. And we'll see how that kind of works out. So in this case, the first step is to neutralize it. And let's say I have 0.1 molar of 50 milliliters of HCN, and let's say I'm adding to this thing 0.1 molar, and I'm only going to add, let's say, 10 milliliters of this guy. So you should note right away they're reacting at 1-to-1 ratios. I should be able to write out the equation for this, which is going to be HCN plus OH negative yields H2O plus Cn negative. Alright, so note I'm doing the net ionic equation there. It's pretty common. And I like to do moles here. I think you have to do moles. But you should realize that in this case my acid is going to be in excess. So I have 0.1 equals 0.05, solve for x, 0.005. This is going to be 0.1 equals 0.01, solve for x, 0.001. Right at 1-to-1 ratios, minus 0.001 to 0, that's gone. And I have minus 0.001. I'm gaining 0.001. Now, you should be aware that this weak acid is pushing in this direction, all right? But the weak, this is the weak acid, this is the conjugate base, and that guy will be pushing backwards, as we'll see in a moment or two. Either way, at this point, I have lost 0.001 of this, I've gained 0.001, and I have 0.004 left. And the last thing we do is divide by the new volume, which is going to be 50 plus 10 is 60, 0.06. So we got 0.004 divided by 0.06 gives me 0.06 moles per liter. And we have 0.001 divided by 0.06 equals 0.016. Okay, so we have, in this case, different concentrations of acids and bases. Okay, so now this is the neutralization half. The second half is, okay, hydrolysis, where the acid hydrolyzes to form acids, H2O plus ions, and the base hydrolyzes back to produce bases. So I have two options here. I have the acid equation that's taking place, or I have the base equation that's taking place. Okay. So in this case, I could say HCN plus H2O yields, I'm going to use two arrows here, H3O plus Cn negative. Or we have Cn negative plus H2O yields HCN plus OH negative. So in this case, note that this is an acid producing an acid and its conjugate base. Here's the conjugate base, reacting with water produces acid and its conjugate and its base. So in some sense, you should note that this reaction is this arrow. The one that's showing is this arrow. But this reaction is actually the reverse of this one. And this reaction on my right side here, this forward reaction, is actually the reverse reaction of that guy. So whenever I write one of them, technically I have written both of them. Okay? So under my initial conditions, I want to write down the concentration for each. I have 0.06 for that guy, and I have 0.016. Well, in this guy, it would just be 0.016 and 0.06. Run the math through, not playing a role, stoichiometric ratio end, not playing a role, minus x, plus x, 0.016 minus x, x. This is going to be 0.06 plus x, x, minus x, plus x, 0.06 plus x, x, 0.016 plus x. Now, because this is an acid equation, we would use a Ka value for this guy, which is going to be, for HCN, 6.2 e to the negative 10th equals x times 0.016, using the shortcut rule here, divided by shortcut rule 0.06. Take a moment. 6.2 e to the negative 10th times 0.06 divided by 0.016 equals x value equals 2.3 e to the negative 9th moles per liter, and that's H plus ions. Now with that, I could leave it as is if that's what the question asks. I could flip it to pH by taking the negative log of that value. Is 8.6, notice for basic. Okay, so in this case, how could I possibly be basic? Turns out that that base here is stronger than the acid. Even though I have a higher concentration of it, it is much more effective at pushing towards products, ever so slightly. So very weak acid in this case. In this situation here, the way I would solve this one would be the Kb. Now the Kb would be Ka times Kb equals Kw. And in this situation, I would say, okay, my 1.0 e to the negative 14th divided by 6.2 e to the negative 10th, and I get my new Kb is equaling 1.62 e to the negative 5th equals my products 0.06 over x, 0.011 with 0.016, same number there. And when you do all the math here, x will equal the concentration of hydroxides. You then take the negative log of that concentration, will give you the POH. 14 minus that value, 14 minus the POH, will give you 8.6. Okay. So here's an example where we have all the math done for a neutralization. Now, in this situation, just drawing a picture of the beaker route, you should note that before beaker of HCN, I'm just going to draw it as HX, another beaker that is OH negative, and then the end beaker, and there's small beakers. Should draw bigger ones. All right, so at this point, I have HX, it's a weak acid, so it's just HX, 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 and I have this many. Hydroxide's a much smaller amount. OH negative, let's just do one of them. Okay, and a cation. So in this case, these two guys react to form X negative, and I have HX, 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 and this is the way you'd want to draw it. You wouldn't have to show necessarily the H plus ions or that nature, but in this case, because we are basic, you could potentially have a very, very, very small amount of hydroxides in there, which wouldn't necessarily be shown as proportional drawing here. All right, let's do another example here, another quick one. I will not walk through all the mathematics again, but we do have some key points here. If I have, let's say, HCN, it doesn't matter what the acid is, plus NaOH. And before I had, in the previous example, I used okay, 0.1 molar, 50 milliliters, 0.1 molar, 10 milliliters. Okay, so I have 0.1 molar of 50 milliliters. 0.1 molar. Now, the amount that I add for this guy is going to be a determining factor. So let's draw two different examples here. Let's say I add, a common point would be 25 milliliters of 0.1 molar. Notice that we are exactly halfway to neutralizing all of it, or 50 milliliters of 0.1 molar. And you'd want to be able to solve out the ice tables for all of these. I will do one of them for you right now, math-wise, okay? And I'm going to be going quicker here. This math is 0.1 equals 0.05 over x. X equals 0.005. So I will add and subtract. So I have hx, I'm just going to call it at this point, plus OH negative yields hx, or x negative, plus water. So I have initially 0.005, and this is going to be half of that. Do the math. 0.0025. Stoichiometric ratio end minus 0.0025 minus 0.0025 plus 0.0025. I have 0.0025 left. This is 0.0025. Divide by the new volume. You'll notice that these two volumes are identical. New volume would be 50 milliliters, 100 milliliters, 0.0 would be 0.1 and 0.1. So 0.0025 divided by 0.1 is just going to be 0.025 moles per liter. 0.025 moles per liter. Now, for this particular problem, we call this, because I am halfway to neutralizing this thing, I call it the half equivalence point. Okay? This is referred to as the 1/2 equivalence point. I have neutralized half of it. At the 1/2 equivalence point, these guys are always the same concentration. Therefore, the Ka value, which is 6.2 e to the negative 10th, equals the concentration of my, in this case, I'm using the hydrolysis equation, so it's HCN plus H2O yields H3O plus Cn negative. I only use my neutralization reaction for the initial neutralization. The rest of it goes off of this guy. My initial amount, 0.025, 0.025, not playing a role, 0 to ratio end. This is going to be minus x plus x plus x, 0.025, x. I used my shortcut here once already. 0.025 shortcut rule. Now I get x, 0.025 here, 0.025 here. So at the 1/2 equivalence point, you'll note that this always cancels, no matter what, every time. So I get, no matter what my starting concentration was, if I go halfway, it always cancels. In this case, the x value, or the concentration of H plus ions, equals 6.2 e to the negative 10th, which was my Ka value. Negative log of that value, which was my Ka value, equals my pH. And at this point, the negative log of the 6.2 e to the negative 10th equals (9.2). Again, we are still basic. Okay. Equal amounts, my base 1. So my base is a stronger base than my acid is an acid. Okay, now picture-wise, how would I draw this? Because I'm at the half equivalence point, all right, the way I would draw this is I'm going to draw Hx. I would draw Hx I just used 4 particles as an example. Now, the same math would hold true if I did an example of HCN 50 milliliters, 0.1 molar, and I added to it NaOH 50 milliliters, 0.1 molar. Okay, so plenty of room now. There we go. All right, so let's do an example of this. Okay, so this is my last example here. We have, in this case, notice all of it's gone. So I have HCN plus NaOH yields H2O plus NaCN. Initial amount 0.005. 0.005. Stoichiometric ratio N 0.005 minus 0.005. Not playing a role. Well, water is just being produced, so he's doing that. Plus 0.005 plus 0.005. This is a weak acid. This is a weak base. 0, 0, and then just 0.005 and 0.005 divided by the new volume would be 0.1 liters. I think I divided by the wrong volume in the last problem, just a heads up, and likely I did because I used that 0.1 twice. Right here, that should be 0.075. So 75 milliliters, not 100. 50 plus 25 is 75. We won't change the numbers a whole lot, but in any sense, actually the answer is the numbers won't change at all. It'll still be the same because it's the half coolants point. All right, so divide by 0.01, and I get this number of 0.05 moles per liter. Now I only have the base, so you can't run an acid hydrolysis equation, HCN plus H2O yields Cn negative plus H3O plus if you have initial value here of 0. It just mathematically starts to clunk out. So whenever you have just the base, which in this case is 0.05, you need to run the base equation. Cn negative plus H2O yields HCN plus OH negative. Initial stoichiometric ratio N 0.05, not playing a role, 0, 0, minus X plus X plus X, 0.05 minus X, X, and X. I have my KB value, which I think I calculated earlier. Not that it matters. Alright. Let's not even worry about it. Let's just redo it quickly here. Okay, so in this case, the Ka times the Kb equals the Kw. The Ka is 6.2 e to the negative 10th, so 1.0 e to the negative 14th divided by 6.2 e to the negative 10th, and I get the, okay, so the Kb equals 1.6 e to the negative 5th equals x squared over 0.05 minus x. Use the shortcut rule here. Times 0.05 equals square root both sides, and I get the x concentration equaling 8.9 e to the negative 4th. Now if I take the negative log of that guy, I will get, in this case, the POH, which is going to be 3.04, and then the 14 minus that value will give me a 10.9 pH, and this is the pH that we call at equivalence. Okay, equivalency, and that is all of the examples you'll get. Thank you very much.